Alright, this is the last section in Unit 1 before your first test. I don't know, maybe there's a test? I don't even know. We'll figure it out. But this is your last section here in Unit 1. We're going to go to Unit 3.5 as well. It kind of does both there. Your homework practice on the right side. Determining vertical asymptotes is what we're going to be doing. Remember, we're doing infinite limits and limits at infinity. Properties of infinite limits and determine some horizontal asymptotes. A limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. So an infinite limit. Okay? Infinite limits, or limit as f of x, a limit as x approaches c of f of x equals plus or minus infinity. They do not exist. We talked about that before in the last couple sections. We just say that the limit equals infinity so we can be more accurate in describing how it doesn't exist. So it might not exist because something is divided by 0, or maybe both sides don't equal the same thing, things like that. There's a jump or a kink or something like that where the limits, it kind of doesn't work out nicely. But if the limit is going to infinity or negative infinity, we can still say DNE, or we can say positive or negative infinity. And we talked about that before. So do not exist is just something that's probably a little better, but plus or minus infinity is okay. This is because the limit must equal a constant number or a constant value. Alright, some real number value. So first, today, I want to determine some vertical asymptotes. Remember, vertical asymptotes are where the denominator equals 0. So I take the denominator and I set it to 0. So I get x minus 2 is equal to 0, x equals 2. So you have a vertical asymptote at x equals 2. No, oh my gosh, I wrote it down wrong. This is 1, isn't it? X equals 1. So you have a vertical asymptote when x equals 1. Then what do I want to do? Well, I want to find the limit as x approaches 1 from the right and from the left. The reason why there's a vertical asymptote. So if I take the limit as x approaches 1 from the left of f of x, I'm actually going to get positive infinity. Okay? If I take the limit as x approaches 1 from the right of f of x, I'm going to get negative infinity. Again, because those two don't match up, we don't have a limit, but that's why we have a vertical asymptote at that point. It's basically what we're doing is one of our functions is going there, and then one of our functions is going there, but it's at x equals 1. For part B, I got to find out when sine of x is equal to 0. Sine of x is equal to 0 when x is equal to 0, pi, 2 pi, and so on. So 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, all the way up. I could say 0 plus 2 pi or 0 plus 2 pi n. I could do that too, but the dot 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 kind of makes sure it mentions that. And then the last one there, I can factor out the top. I get x plus 4, x minus 2, and then the bottom is x minus 2, x plus 2. So the x minus 2's cancel. That's the whole. Okay, that's a whole. That's a removable discontinuity. But you have a vertical asymptote when x is equal to negative 2. So you have a vertical asymptote when x is equal to negative 2. Pretty easy. Again, we've done that stuff before, so it's not that big of a deal. Properties of infinite limit. It's very similar to properties that we've had of everything else. So if f of x goes to infinity and g of x goes to some value L, when I take the sum or difference, if f of x is infinity, plus or minus whatever that L is. Okay? But infinity plus L is probably still going to be infinity, right? So this is still infinity. F of x times g of x. So this is also going to be infinity whenever L is greater than 0. If it's less than 0, it's going to be negative infinity. Okay? F of x over g of x is infinity over L, which is just infinity. Okay? And then L over infinity is going to be 0, right? Because the bigger the bottom gets, the top stays constant, right? So the bigger the bottom gets, it's approaching 0. And the same thing here, with the bigger the top gets, when the bottom stays the same, it's getting bigger and bigger and bigger, so it's approaching infinity. We got some limits at infinity. Okay, let's see what we got here. We got 3x over x squared plus 1, and I want to find the limit at negative infinity, and I want to find the limit at positive infinity. Well, because this function, okay, it kind of looks like a v here, but these values, see if I can do this pretty nicely, but it's good so far. That's pretty good. It's approaching positive 3 in both directions, so the answer is going to be 3 in both directions. They do not always have to be the same, so they don't always have to be the same. They just happen to be in this case, but they don't always have to be. And you can see definitely from the table that it's approaching 3 and it's approaching 3. Okay? Pretty simple. I mean, it makes sense. It makes sense that it would, right? Now, if we want to find the limit of a function at negative infinity or at infinity, we're talking about end behavior. End behavior is talking about a horizontal asymptote. Horizontal asymptote. Okay? So we have some theorems. We have, if r is a positive rational number and c is any real number, then the bigger the bottom gets divided by the top, it's going to be 0. Okay, whether it goes to positive or negative. So if it's, doesn't matter which way it goes, as long as the bottom value is growing really, really large, really fast, but the top stays the same, it's going to approach 0, no matter if we're approaching negative infinity or positive infinity. And with horizontal asymptotes, so here's some things with that, right? With horizontal asymptotes, I just want to make sure we write them down correctly here. So if the top is bigger, it's either going to be positive or negative infinity. Okay, it's the exponents, right? So the top exponents. Well, let's just say top. If the top grows faster, grows bigger. So this is, we'll talk about growth. We'll just do that. We'll talk about growth. If the top grows faster, then it's positive, negative infinity. If the bottom grows faster or bigger, then it's going to be 0. Okay, the bottom is going to be really, really large, while the top stays the same. It's approaching 0. And then what happens if they're the same power? Then we just divide the coefficients. So we divide coefficients. You should probably remember that from last year as well, but that's basically what's going on. So in this case, we're approaching infinity. The powers are exactly the same. So this is 1 and this is a 1. The negative 1 and a positive 1 don't really matter because they're always constant. They're always going to stay there. The x's are what's going to grow. So the positive, negative numbers at the end, the constants at the end don't matter. Or they don't matter as much. So because these are the same, it's the ratio of the coefficients. So it's 2 divided by 1. So that's just 2. This one here is positive infinity. The 5 and the 1s don't matter. The x and x squared. This one's not growing fast. So this one's going very, very small. And this one's going much faster. So because the bottom is bigger, this one's going to 0. And this one here, yes, these are the same, but this is bigger. This is growing much faster than anything else. So because that x to the 4th is growing faster than anything else, this is going to be positive infinity, even though it's approaching negative infinity. If this was an odd power, like 5x to the 5th power, then this would be negative infinity because a negative to the 5th power is still negative. So we got to watch for those positive pluses and minus signs with the infinities. But other than that, that's not too bad. Now you might see an example in the book where it wants you to do find the limit without using necessarily horizontal asymptotes. At infinity, it wants you to use actual algebraic thinking. So I'm going to do probably A and B for you. Part C is a little more difficult, but Let's do A and B for you. So basically what you're doing is this is the algebraic way to find the limit instead of just using horizontal asymptotes. You're taking your original function, 2x, okay, minus 1, and this is your denominator is x plus 1. And I'm dividing it by the x. Because they're both the same, I'm taking and I'm dividing everything by that x. Okay, so what's going to happen? Well, this is going to be the same thing as the limit as x approaches infinity of 2 minus 1 over x divided by 1 plus 1 over x. Okay, so we can then say, okay, well, this is 2 minus 0, because if I plug in infinity, we know that goes to 0. If I plug in infinity there, that also goes to 0, so that's 1 plus 0. So I get 2. Okay, so that's the algebraic way to do that. I would not be too concerned with that. I would definitely use the horizontal asymptote method, and I'm not even going to do part B and C. I don't even care about that, but that's just that way of thinking. It's not that big of a deal to not remember how to do that, so don't worry too much about that. Infinite limits with trig functions. We got a couple more examples to go, and then we'll be done with this one. So the limit as x approaches infinity of sine of x. What do we know about this function? Well, we know this function actually goes up and comes down and goes up and comes down and so on all the way through the whole graph. And so because it's going to infinity, you don't know, it oscillates between 1 and negative 1. So like this is positive 1, this is negative 1, and depending upon what value you pick, it's never going to come together to a separate value. So this one here is going to be a DNE because we do not know what it's going to oscillate to. It could be positive 1, negative 1, it could be anything in between. It's never going to come to a clear-cut value because infinity is always going to be larger than any other number you can pick. So that one there is DNE because it's oscillating. Next one here, sine of x over x as x approaches infinity. So this graph, if I look at it, it goes up and down and up and down and up and down. So it starts off with a nice kind of positive 1 and a nice negative 1, but then it gets smaller and smaller and smaller and smaller as it goes out, and it actually, the further and further you look at it out, it's actually going to approach 0. So this is going to be 0. It oscillates, but because it gets smaller in that oscillation, that it's always going to approach some value. It's going to kind of mellow out. It's not going to be as a really high oscillation, and because of that mellow out factor at infinity, it's going to equal 0. And if we wanted to actually use the squeeze theorem from the last section, we could go ahead and do that. I'm not going to do that, but we could definitely use the squeeze theorem on that, and you probably will in your practice problems. And the last ones here, oops. Okay, so this function, it's e of x and ln of x. So if f of x equals e to the x looks like this, okay, where it crosses at 0, 1. And f of 0 is equal to 1, because I can plug in 0 and I get 1. F of 1 is just e to the 1, which is just e, which is like 2.718, something like that, okay? The limit as it approaches infinity of f of x is going to actually approach infinity, because this is going to keep going and going and going without bound, and so it's going to be infinity, and then negative infinity, e to the negative infinity, ooh, so that's not an infinity symbol at all, there we go, is going to be 0, because e to the negative infinity is 1 over e to the infinity, and this grows without bound, so it's 1 over infinity, which that's why it's going to be 0. The ln function, which is the last set that we're going to work on, is the inverse of e. Remember, flipped around the y equals x line. Okay, so it is going to be like there, and this is going to be your 0, 1. All right, so g at 0 is equal to 1. G of 1 is equal to the ln of 1. Oh man, I don't know what I'm doing. I got to back up a little bit. Here we go. Okay, g of 0 is not existing. It does not exist because this y-axis acts as a vertical asymptote, so it does not exist at that point. But g of 1 is equal to 0 because the ln of 1 is equal to 0. That's something we got to know. If you don't want to understand how to do it, ask me in class, but that's not that big of a deal. You should already know how to do that from last year. The limit of g of x as x approaches infinity is going to be infinity, because it's the ln of infinity, which is equal to infinity. This arrow goes on forever. It will eventually reach the highest point, infinity, on the y side, but it's going to take very long to get there. Whereas e grows substantially faster. The ln grows really small, but it will eventually get there. And then the limit of g of x as x approaches 0 from the left, or from the right, I'm going this way down. So that's going to be negative infinity, because it's, again, going down and down and down. So that's it. That's this video, I think. This is the last video in this unit. You might or might not have a test after this. I don't remember, but I'll let you know in Power School. Ask questions if you need any help, and other than that, deuces.